Welcome to the Future Ready podcast from Siemens. We have another great guest to talk about the transition to software-defined, Alastair Orchard. He's the Vice President of Digital Enterprise at Siemens, as well as the CTO and co-founder of Timax.cloud. Thanks for being here, Alastair.
Sure. Hi, Nick. Pleasure to be here.
So I think for a lot of people, when they think Siemens, they think of the hardware we make and deliver. It might be the trains, the turbines, the medical equipment from our sister organizations, or the programmable logic controllers in production environments. But it's often hard to see the software, whether it's the software aiding these hardware products or what we do with design and manufacturing tools. This part of our business can be easy to miss if you're not interacting with it on a daily basis. But some of that's the point, to get out of the way of the healthcare professionals, manufacturers, engineers, designers. But there's an evolution taking place, and we've been talking about it a little bit on the podcast, and it's super important to producers, especially software-defined automation and the broader growth of software across industries. Alastair, would you mind painting a picture of what this shift looks like for our audience?
Okay, so I don't know how old you are, Nick, but I was born in the 70s. I think I'm a bit older than you, right? I'm basically a Gen Xer, so I was born into an analog world that you probably kind of never experienced. And then I grew up during the digital revolution. And now, I live together with you in this software defined society. And there's nothing particularly unique about that. I think this probably describes a billion people. But in some ways, it provides me with something of a different perspective. If I'd been born earlier, obviously, I'd have missed this transition to digital completely. But I think younger generations, and I was thinking of my kids, but this may actually apply to you as well. I think they often find it difficult to grasp what actually living in a hardware-defined world was like, and just how dramatic this transition's been. And in fact, you call this transition a shift, as though it was a sudden thing, and I think it's exactly right. But I like to equate that shift to maybe a compressed evolution of life on Earth. It's slightly strange, but if you go back far enough, then all the animals on the Earth basically had kind of hard-coded behaviors, and that's where the analogy comes in. They operated, let's say, on just inbuilt innate instincts that were hard-coded, defined in their genes, the ones that they inherited from their parents. And they had brains, obviously, just like our modern equipment has brains, capable of kind of interpreting simple sensor information, reacting to input. But those actions were really, I'd say, predetermined. So it was, I guess, a predictable world. Species evolved to fill a niche. Animals kind of lived within that niche. And any abrupt change really, in the conditions, it would cause actually an extinction, okay? And then humans evolved and everything changed. So we were, and we still are, kind of slower, weaker, and squishier than average animals. But as you know, our big advantage was our brains, right? So in the place of pure mechanics, emerges this operating system that could generate a world model. And that world model had predictive power, allowed us to think. This substrate was actually programmable as well. That's the real advantage. We could learn. So if you fed that brain information, then it could learn to use tools, communicate, plan, and adapt in real time to any challenges we're presented.
Yeah, you didn't need the generations to evolve that tool use. You could learn it from one of your fellow humans next to you, sitting at the campfire.
Exactly. So it's the key here is adaptation, but it's also speed. So you're absolutely right. And then we have memories, obviously. So we can store and retrieve these software programs that we've learned and that we learn from other people. And those collaborations actually allow us to perpetuate this learning over kind of multiple generations. So slightly strange analogy, but of course, when we start to look at, if we jump into industry, let's say, then we had this industrial revolution. It created this Cambrian explosion of specialized machines. And that's what we find very often filling our factories today. They evolved to operate in a dedicated niche. And honestly, they're all subject to extinction if conditions changed. And And digitalization, this transition, it's again helped transform that substrate, and so we're now able to kind of embed compute and communication capabilities in just about everything. What we have is a kind of industrial operating system, and we can use that to create these world models, just like our brains do. We call them digital twins, and we can use software logic to program adaptable behavior at every rigid juncture and really start to transform all of that specialized hardware to become repurposable, software-defined, and universal.
So you mentioned digital twin there. Usually I kind of think of that as a mirror held up to reality, kind of fed by IoT data, useful for transparency, capable of predicting maintenance conditions, right? Is that what you're talking about?
Sure. That's certainly one application. I think that's a limited view, though. You're kind of presuming that a digital twin is just a shadow. You said mirror. That's the same kind of thing of an existing asset, of a real asset. And that's certainly true. And it's certainly useful in brownfields. So where legacy or existing machines need optimizing. But, a digital twin's at least as important when it's also used to optimize a design before it's built. This is actually the Siemens special source. It's this idea of shifting left and starting in the virtual world. So we spent really decades creating these multi-physics environments that really accurately model the dynamics of the real world. Okay, and this means our customers can design, build, and test really anything: an airplane, pair of sneakers, personalized medicine, a computer chip, or a production machine. And they do that in this simulated reality, so that they're sure of what it's going to cost, whether it's manufacturable, what the performance will be, what the maintenance intervals will be, and everything before they ever actually commit resources in the real world. So it's very powerful. And if they're careful enough to make the behavior that they model adaptable, I mean, this is the exact opportunity at design phase, then what they can do with that digital twin after is to actually embed it in the machine itself or the product itself. It kind of acts as the code behind the product's operational behavior, so that it can actually continuously adapt. And then, of course, it can also act as that digital mirror you mentioned in the question.
Okay. Thanks for that. So when we were talking prior to the recording, you framed this idea in a really interesting way around a self-driving car. How does that autonomy in a vehicle translate to manufacturing and a software-defined mentality?
Yeah. Do you mind if I go back through that analogy or that example? Software defined, and actually the whole concept of this virtual real duality. And this is really a story of when companies first started to look at building self-driving cars. And actually, they couldn't really imagine how difficult it would be at the time. You've probably heard of Elon Musk talking about this. Getting the basics right is actually quite easy. But there's this 80% very quickly, and then there's this long tail of edge cases that are really almost impossible to predict. And it actually takes literally billions of miles of driving on public roads to gather all of this experience, and that takes just far too long. So the answer was actually to step into the virtual world, to generate myriad kind of virtual environments. And again, these are multi-physics environments. So, and then we fill them with literally millions of virtual cars. And then they play out this interaction, complex traffic scenarios and everything in what's really complete safety, because they don't really know their virtual cars or that their journeys are kind of happening in this what's really a video game. And the reason they don't know they're virtual is that we kind of equip them with digital versions of all of their sensors, so they can see the street ahead of them. They can see the obstacles. They can see other cars. And these sensors, although they're virtual, they're fully operational. Then we use like real-time ray tracing to ensure that the light sources bounce off objects in really natural ways. And this makes a big difference if there's water on the street or if there's low sunlight or whatever. This creates reflections that actually do affect the sensors, and that would create chaos in the real world if they hadn't already encountered it and learned how to deal with it. And then we model friction, momentum, gravity, inertia. It's an incredibly accurate world. And then we can turn on the rain, we can make it foggy, we can have kids run out from behind buses. And at the beginning, you really get a lot of accidents. But each one improves the model, and then each of those learnings is actually replicated to all the other virtual cars. And so the swarm, let's say, learns at a really incredible accelerated rate. And the key to that, so that's all in the virtual world. And then once the error rate, let's say, once the incident rate drops beyond a threshold, then the model's actually compiled and sent into the brain, into the AI chip in the real cars. And then it uses this executable digital twin to drive and guide itself in real streets. So we've transitioned from virtual to real. And again, we've done it faster and safer than it could ever be done in a purely physical world using physical experiments.
Okay, and then that links to what I thought digital twins were, where you have all of the extra data happening during operation impacting the model of the design of the processes. Can you talk a little bit about the operation side?
Yeah, so you raise a really important point there, and that is those models are not static. So we talk about this life cycle of the digital twin, and we've discussed a couple of these things. So we've discussed when the digital twin's born in the virtual world, when it transitions into reality and starts helping operate and guiding and optimizing the operations of a machine. But I think you used the IoT word at some point, this Internet of Things. This is essentially the ability to pick up data signals from sensors, in this case in the car, and feed the results back into the either into the model so that it can react directly, but also back into the training data so that these models can continuously evolve. Every accident that then occurs in reality is going to improve that, and you see the error rates fall even further.
Okay. So going back to manufacturing, kind of what we want to talk about today, is this pointing businesses at possible solutions on the production lines, like slower unit times or vibration readings indicating a match to previous maintenance needs? Or is it something bigger?
It's certainly that, but it's also something bigger. When we refer to software defined, you might think that this is kind of happening on a single level, so a single use case, but it's more powerful than that because it's recursive. So in the same way that you might think of hardware components being, I don't know, assembled or combined into sub-assemblies and then a physical system like a car, so software can and really should be used to operate and optimize these nested processes at many levels, if that makes sense. So maybe one level is that vibration of a component, but then that component is actually sitting in a machine. And so our digital twins, our software, is helping optimize the parameters being fed into that machine. But it's also orchestrating the journey of the products being manufactured in that facility, orchestrating the journey of the product between the machines in the factory. And if you think of that factory as one of a network of facilities, then software is also optimizing the dynamics of the complete supply chain. And these things, they're nested, they all interact. It's modular, it becomes a big, living, dynamic system. And really, the point is that when you define something in software, whether it's that component, the behavior of the machine, all the way up to an entire network, It can be infinitely adjusted and repurposed. You're never painting yourself into a corner. Although I have to say, it's kind of ironic because we're generally eager as engineers somehow, maybe the older ones,
To make the box.
to make the box, yeah, to permanently fix this into hardware so that you can automate it and forget it. But that is the old way of thinking. We obviously need hardware, right? Hardware is our interface to the real world. It's what we use to transform raw materials into finished goods. But let's say the mindset shift here is that we need to ensure there's as many degrees of freedom as possible left at every level. So whether it's the component or the machine or the line or the factory or the supply chain remains adaptive and programmable.
Well, it's really interesting that you're talking about looping in more of a business into the digital twin, like the unified context for products and processes. How far does that thought extend? How far are we pushing that workflow?
Well, yeah, it's pretty pervasive. We call it software-defined X for a reason. And it's not actually unique to exactly manufacturing. So, ERP companies, they've sold their platforms as these software-defined processes for years. You might have heard of some of these: order to cash, hire to retire. These are processes, and we really do the same along the innovation axis. That's what Siemens really does. So our business process, let's say, is idea to cash, if that makes sense. And we can break it down further. So you can go, if you start with the idea, then we're talking about a software-defined process that turns or transforms that idea into a requirement. Turns that requirement then into a specification, a detailed description of what we want to achieve. Then that specification gets turned into a design. Along the way, that design gets validated, tested in the virtual world, and fully validated. We then turn that design into a plan, and then the plan into a product, and then the product into revenue. Okay, these are kind of milestones along the life cycle of the digital twin. We talked about this life cycle before, and it's kind of formalized into this software-defined business process. Sometimes we call that the digital thread that links what's basically a market signal to revenue on the other end. And the more hard-coded steps there are, the more manual interactions and the more disconnections that you find along the way, the longer and more costly that journey will be. And that's why it's frustrating, actually. That's why the process of bringing an idea to market, it should really only take 24 hours for a fully defined, software-defined and executed process. But today, it often takes some of the biggest companies in the world 24 months or more. And of course, they're using software. So obviously, software isn't a panacea here. It's not the only factor. If you take that software and write inflexible code with it, then that's just about as bad as building it into inflexible hardware. So it's adaptability the whole way.
Yeah, if you hard code a number. If you hard code a number rather than using a variable, that's just so bad.
Yeah, that's actually best practice. So it's not hard coding numbers, it's not hard coding interactions, and it's not hard coding behaviors. Yeah, good point.
I think that is a perfect point to end on for today. So I still have so much to talk with you about, Alastair, but let's save it for part 2. I'm really curious to understand what it looks like for our customers from your perspective. And thanks to the audience for tuning in. We'll be back soon with Alastair Orchard to talk about software-defined a little bit more and its role in industry. Make sure to hit that subscribe button to get a notification for future episodes. And until then, check out the episode description to learn more.